Hello, this is Coach Meidenbauer for AP Pre-Calculus. Going to go over topic 1.1, change in tandem. Okay, so we're going to talk about changes with functions and different types of functions, whether they're analytical, graphical, numerical, verbal. We'll do with tables another day. So a function is a mathematical relation that maps a set of input values to a set of output values. So a couple of important vocab words here that we need to know is that if we have an input, that's going to relate to our x variable for what we're going to be dealing with today. Sometimes the input is t for time, and this is also going to relate to our domain. And then if we see the word output, that's going to relate to our very good y. Okay, so these set of input values, and these kind of went through the bullets already here. But the set of input values is called the domain of a function. The set of output values is the range of the function. The variable representing the input is called the independent variable. So input independent, output is dependent. And then I talked about how these can be represented differently. So pretty much, I think this is mostly the same function here. So we have analytical. So if the input value is 5, what is the output value? So for this function, and it's giving us 200 plus 10x. So what this input value means is this is x equals 5. So f of 5 is equal to 200 plus 10 times 5. What is 10 times 5? Very good. It's 50. 200 plus 50 is 250. Okay. Graphical. So here's a graphical representation of the same thing. So input of 5 is right here. And that height, this doesn't necessarily say it's the same function, but it is. So this is going to be an output of 250. So graph the point. So this is going to be the point 5, comma 250. Numerical, it can be represented different ways. They do represent this one as a table. Numerical, they can just list the points as well as a table. So complete this, and this is just using this function right up here. So it's a linear function, and the slope is 10, so it's going to increase by 10 every one value. So this is going to be 210, 220, 230, 240. And there are 200 people in a small concert venue. The gate allows 10 people to enter every minute. Write a function in terms of t, where t represents the minutes and c of t represents the number of people at the concert. So our input here is, instead of x, is going to be t. Okay, so our input is t. So c of t is equal to, we start with 200, and we increase by 10 people every minute. So that's going to be our function representation verbally. Okay, so those are different things. This should be nothing new. Just kind of getting us back in the swing of things here. A little bit of new stuff coming up here, not quite with the increase and decreasing, but a graph intersects the x-axis and the output value is 0. So that's known to be the zeros of the function. That's just vocabulary that you should already know. The zeros of a function is when y is equal to 0. Function is increasing over an interval of its domain if as the input value increases, the output values increase as well. So as you're going from essentially left to right of a graph, if the output value is getting larger, we're increasing, and we can only increase in pre-calculus. It just wants to increase inside the interval, not on the interval. Decreasing is when the output values get smaller as we go from left to right. Okay, so we have two examples right here. One is increasing, one is decreasing. These are linear, so it's very easy to tell from the slopes. But the increasing function is always increasing. The decreasing function is always decreasing. But when we start getting parabolas, it'll increase and decrease certain things. Okay, so example down below, it's just true, false. Here's our graph. This is actually a piecewise function. It doesn't tell us exactly what the piecewise function is, but it does give us a graph of it. So f increases from -5 to -2. I'm going to real quickly, I'm going to trace these so that you can kind of see. So going from left to right, what's happening to those values on f? Are they getting larger or smaller from -5 all the way to 2? You said smaller, so that means that we are actually decreasing. So this is false. We are decreasing. All right, let's go ahead and go to the next one. We'll do orange. What about increasing from 0 to 2? Is that true or false? If you said false, you'd be wrong. It is true. We are increasing. Those output values are getting larger from left to right as we look at our graph. What about, we'll do red now. F increases from 0 to 5. So here we go. As I went from left to right, the entire time it was increasing. Okay, so this is true. The next one in blue, F decreases from -2 to 2. So far it looks good for decreasing, and then, what does it do? Then it increases. So F decreases, then increases. So it's not decreasing the entire time. This is going to be F for false. F has zeros at plus and minus 2. So we'll do this one in green now. So we're looking at plus and minus 2. Does the function equal 0? The height is 0 at plus and minus 2 for x. That is totally 100% true. All right. Oh, are there any questions? Okay, good, because you can't ask any. Now we're going to talk about concavity. This may or may not be new to you. So graph of a function is concave up on the intervals in which the rate of change is increasing. So please know that concave up is when the rate of change is increasing. Concave down is when our rate of change is decreasing. These are two things that you need to absolutely memorize. Now, visually, what does this look like? Well, on our concave up example, as we go from left to right, our rate of change here is indeed increasing. What that means is if I were to draw two lines from here to here, the same, so from -3 to -2, and then from -2 to -1, that slope would be getting smaller. And then from -1 to 0, sorry, not smaller, that slope is getting larger because it's very negative for the first segment, and then somewhat negative on the second segment, less negative on the next segment. And then from 0 to 1, we're going more positive. Essentially, the slope gets steeper and steeper as we go through here. So that means we're concave up. Now, if you look, up starts with the letter U. No, this is not kindergarten. Up is the letter U. Guess what that function, that parabola looks like? It looks like a U. So if you see something that's in a U function, it's going to be concave up. Okay. And then concave down, that's when our rate of change is decreasing. Oh boy, I forgot to pay the electric bill. I'm sorry. Hold on one second. Let me pay that bill. And we're back. So as we go from -3 to -2, those heights, it's going to get less and less steep as we go through. So that's pretty steep. Actually, I don't want to talk about steepness. No, it's not steepness. The rate of change is getting smaller. So this is like a slope of like pretty big, maybe like 3 or 4. That slope is a little bit lesser. It's hard to tell, but trust me, it is. That slope is even less. The slope is actually getting negative now, so it's certainly less on the other side. So it's kind of the idea, is that we are getting the rate of change is getting smaller and smaller, being negative numbers as we connect those lines. Okay, so concave down ends in an N, and that looks like a lowercase n. Okay. Also, we can think of it this way: concave up like a cup. Okay, a cup can hold water. If it's concave up, it's like a cup. What rhymes with down? I know, frown. Concave down like a frown. A frowny face is concave down. All right, you know what? I'm moving on. I didn't say my material was any good. All right, so given the graph to the right, we have g of x right there. We got a lot of weird things going on there. It looks like we got like a piecewise function. Looks like we have two parabolas and a semicircle. Here we go. G increases from 2 to 6. I'll do the same underlining thing I did before. So from 2 to 6, G increases. Let's go ahead and look at that. From 2 to 6. Is that true? Does it increase on the entire interval? No, that is false. G is concave down from 0 to 2. From 0 to 2. Looks like this. That little green part only that I just shaded. Is that concave down? That looks like it's up like a cup. It's half of a U, so that's going to be false. That thing is concave up. Let's do now. Go orange. Concave up from -6 to -2. That totally looks like it's concave up. That rate of change is increasing as we go through. So that is true. It's up like a cup. Some compound one. So we need these two statements to be true as we go through it. G decreases and is concave up from -2 to 0. So from -2 to 0 is right here in red. That decreases. I 100% agree. So decreases. That is totally great. Is it also concave up for that red part that I just drew earlier? Yes, that is concave up. Okay, it looks like a half a cup. So that is indeed true as well. So we are true all the way through. G has zeros. I'll do this in, I'm not blue yet. G has zeros at plus and minus 2. That's true. See that? And plus and minus 6. I see that. Graph crosses the x-axis or touches the x-axis at those points. That is certainly true. Last but not least, it looks like it's another compound one. What color haven't I done yet? I'll go with the gray. So we need G to be decreasing at a decreasing rate. So from -6, where am I? I'm from here. -6, -4. This gray part right there. It does decrease. G is decreasing at a decreasing rate. What the heck does that mean? We need to translate that. If we go back up here, if our rate of change is decreasing, we are concave down. So at a decreasing rate, that means we are concave down. Are we concave down from -6 to -4, which is that gray segment? No, we are not. So that part is not true. That is not true. So this is going to end up being false. And that is going to wrap up our lesson here with 1.1.